To determine the appropriate fuse disconnector size, consider the following factors: transformer rating, which is 10 MVA in this case, voltage levels, with a primary voltage of 11,000 volts and a secondary voltage of 3,800 volts, and the short circuit current. The short circuit current through the fuse disconnector will depend on the available fault current at the location. This information should be provided by the power source. Also consider a safety factor. To allow for safety margin and potential load growth, a safety factor of 1.25 is typically used. The fuse disconnector size can be calculated as follows: fuse disconnector rating in amps equals transformer rating in volt amps times safety factor divided by primary voltage in volts times the square root of 3. Here is an example. Assuming a short circuit current of 25 kiloamps, fuse disconnector rating in amps equals 10 million volt amps times 1.25 divided by 11,000 volts times the square root of 3. Fuse disconnector rating in amps then equals approximately 65.6 amps. Therefore, the appropriate fuse disconnector size for this installation would be 65.6 amps. Additional considerations include ensuring the fuse disconnector has an interrupting rating sufficient for the available fault current. Use fuse links with a current rating that matches the fuse disconnector rating and install fuses on both the primary and secondary sides of the transformer. Follow all applicable electrical codes and standards for the installation and maintenance of fuses and fuse disconnectors. Let's elaborate on each of these points to provide a comprehensive understanding. The transformer rating is a crucial starting point because it defines the apparent power that the transformer can handle without exceeding its design limits. In this case, a 10 MVA transformer is substantial and typically used in industrial or utility applications. The MVA, or megavolt amps, is a unit of apparent power, which is the product of voltage and current. It's important to use volt amps instead of watts because transformers also deal with reactive power, which doesn't contribute to actual work done but still affects the current flowing through the system. Understanding the voltage levels, both primary and secondary, is essential for selecting the correct fuse disconnector. The primary voltage, 11,000 volts, is the voltage on the input side of the transformer, where power is received from the source. The secondary voltage, 3,800 volts, is the voltage on the output side, where power is delivered to the load. These voltage levels dictate the current that will flow through each side of the transformer for a given power rating. The short circuit current is perhaps the most critical factor in fuse selection. It represents the maximum current that can flow through the circuit during a fault condition, such as a short circuit. This current is many times higher than the normal operating current and can cause severe damage to equipment if not interrupted quickly. The short circuit current depends on the impedance of the power source and the impedance of the transformer itself. Utility companies or grid operators typically provide this information, as they are responsible for maintaining the stability of the power grid. The fuse disconnector must be able to safely interrupt this fault current without failing or causing an arc flash. A safety factor is applied to the calculated current to account for uncertainties, potential load growth, and variations in operating conditions. A safety factor of 1.25 means that the fuse is sized to handle 125% of the calculated current. This provides a buffer against nuisance tripping and ensures that the fuse will not be overloaded under normal operating conditions. The formula for calculating the fuse disconnector rating combines all of these factors into a single equation. It ensures that the fuse is sized appropriately to protect the transformer from overcurrent conditions. The square root of 3 in the denominator is used because the primary voltage is typically a line-to-line voltage in a three-phase system. The example calculation demonstrates how to apply the formula to a specific scenario. In this case, the calculated fuse disconnector rating is approximately 65.6 amps. However, it is important to select the next standard fuse size above this value, which would typically be 70 amps or 80 amps, depending on the available fuse sizes. The additional considerations are equally important. First, the interrupting rating of the fuse disconnector must be greater than the available fault current. This ensures that the fuse can safely interrupt the fault current without failing. Second, The fuse links must be matched to the fuse disconnector rating. Fuse links are the replaceable elements within the fuse disconnector that actually interrupt the current. They come in various current ratings and time current characteristics, so it is important to select the correct fuse length for the application. Finally, fuses should be installed on both the primary and secondary sides of the transformer to provide comprehensive protection. This protects the transformer from faults originating on either side of the system. It is crucial to follow all applicable electrical codes and standards, such as the National Electrical Code, or NEC, and the standards set by organizations like the Institute of Electrical and Electronics Engineers, or IEE. These codes and standards provide detailed requirements for the installation and maintenance of fuses and fuse disconnectors, ensuring that the system is safe and reliable. For example, NEC Section 450.3 addresses the protection of transformers and provides specific requirements for overcurrent protection based on the transformer's voltage and impedance. NEC Table 450.3 provides the maximum rating or setting of overcurrent protection for transformers rated 600 volts or less, while NEC Table 450.3 B provides similar information for transformers rated over 600 volts. These tables specify the maximum allowable percentage of the transformer's rated current that the overcurrent device can be set to trip. The NEC also requires that the interrupting rating of the overcurrent protective device be sufficient for the available fault current at the transformer's location. This is to ensure that the device can safely interrupt the fault current without failing or causing an arc flash. In addition to the NEC, IEE standards also provide guidance in the selection and application of fuses and fuse disconnectors. For example, IEE Standard C37.41 provides testing requirements for distribution cutouts and fuse links, while IEE Standard C37.42 provides specifications for high-voltage fuses. These standards help to ensure that fuses and fuse disconnectors meet certain performance criteria and are suitable for use in electrical power systems. When selecting a fuse disconnector, it is also important to consider the environmental conditions in which it will be installed. Factors such as temperature, humidity, and altitude can affect the performance of the fuse disconnector. For example, high temperatures can cause the fuse link to direct, meaning that it will trip at a lower current than its rated value. High humidity can cause corrosion, which can also affect the performance of the fuse disconnector. Altitude can affect the dielectric strength of the air, which can reduce the interrupting rating of the fuse disconnector. Therefore, it is important to select a fuse disconnector that is suitable for the specific environmental conditions in which it will be installed. Regular maintenance is also essential for ensuring the reliability of fuses and fuse disconnectors. This includes inspecting the fuse disconnectors for signs of damage or corrosion, testing the fuse links to ensure that they are still within the rated values, and tightening the connections to prevent overheating. It is also important to replace fuse links that have been blown or that are nearing the end of their service life. In addition to these general guidelines, there are also some specific considerations for selecting fuse disconnectors for transformers with unusual characteristics, such as transformers with high inrush currents or transformers that supply nonlinear loads. High inrush currents can occur when a transformer is energized, and they can cause nuisance tripping of the fuse. To prevent this, it is necessary to select a fuse with a time delay characteristic that can withstand the inrush current without tripping. Nonlinear loads, such as variable frequency drives, or VFDs, can generate harmonic currents, which can also cause nuisance tripping of the fuse. To prevent this, it is necessary to select a fuse that is specifically designed to handle harmonic currents. In summary, selecting the correct fuse disconnector for a transformer is a complex process that requires careful consideration of several factors, including the transformer rating, voltage levels, short-circuit current, safety factor, environmental conditions, and any unusual characteristics of the transformer or its load. By following these guidelines and consulting with a qualified electrical engineer, it is possible to select a fuse disconnector that will provide reliable protection for the transformer and the electrical system. Let's further expand on the practical aspects of fuse disconnector selection and installation. Firstly, it's vital to understand the different types of fuses available. There are various fuse types designed for specific applications, including time delay fuses, fast-acting fuses, and current-limiting fuses. Time delay fuses, also known as low-blow fuses, are designed to withstand temporary overloads, such as motor starting currents, without tripping. These are suitable for circuits with inductive loads that draw high inrush currents. Fast-acting fuses, on the other hand, are designed to trip quickly in response to overcurrents. They are used in circuits where sensitive electronic components need to be protected from damage due to rapid fault currents. Current-limiting fuses are designed to limit the magnitude and duration of fault currents. They are used in high fault current applications where it is necessary to minimize the potential for damage to equipment. The selection of the appropriate fuse type depends on the specific characteristics of the circuit being protected. Another crucial aspect of fuse disconnector selection is the interrupting rating. As previously mentioned, the interrupting rating of the fuse disconnector must be greater than the available fault current at the installation location. The available fault current is the maximum current that can flow through the circuit during a fault condition. This current is determined by the impedance of the power source and the impedance of the circuit being protected. The interrupting rating of the fuse disconnector is the maximum fault current that the fuse can safely interrupt without failing. If the interrupting rating of the fuse disconnector is less than the available fault current, the fuse may rupture or explode during a fault condition, which can cause serious damage to equipment and personnel. Therefore, it is essential to select a fuse disconnector with an interrupting rating that is greater than the available fault current. When installing fuse disconnectors, it is important to follow all applicable electrical codes and standards. The NEC provides detailed requirements for the installation of overcurrent protection devices, including fuse disconnectors. These requirements cover topics such as the location of fuse disconnectors, the wiring of fuse disconnectors, and the grounding of fuse disconnectors. It is also important to follow the manufacturer's instructions for the installation of fuse disconnectors. The manufacturer's instructions will provide specific guidance on how to install the fuse disconnector correctly and safely. In addition to following codes, standards, and manufacturer's instructions, it is also important to use good electrical practices when installing fuse disconnectors. This includes using the correct tools and equipment, wearing appropriate personal protective equipment, and verifying that the installation is correct before energizing the circuit. Proper torque is crucial for ensuring a reliable electrical connection. Over-tightening can damage the conductor or the equipment, while under-tightening can lead to loose connections and overheating. Torque specifications are typically provided by the manufacturer of the equipment and should be followed carefully. Regularly inspecting and maintaining fuse disconnectors is crucial for ensuring their continued reliability. This includes visually inspecting the fuse disconnectors for signs of damage or corrosion, testing the fuse links to ensure that they are still within their rated values, and tightening the connections to prevent overheating. Fuse links should be replaced when they have blown or are nearing the end of their service life. It is also important to keep fuse disconnectors clean and free from debris. Dust, dirt, and other contaminants can accumulate on the fuse disconnector and reduce its performance. The frequency of inspection and maintenance will depend on the environmental conditions and the operating conditions of the equipment. However, as a general rule, fuse disconnectors should be inspected and maintained at least annually. When replacing fuse links, it is important to select the correct fuse link for the application. Fuse links are available in a variety of current ratings, voltage ratings, and time current characteristics. The correct fuse link must be selected to provide adequate protection for the circuit being protected. It is also important to ensure that the fuse link is compatible with the fuse disconnector. Fuse links and fuse disconnectors are designed to work together as a system, and using incompatible components can compromise the safety and reliability of the installation. In addition to these practical considerations, it is also important to be aware of the potential hazards associated with working with fuse disconnectors. Fuse disconnectors are part of an electrical system and can pose a risk of electric shock or arc flash if not handled properly. Therefore, it is essential to follow all safety precautions when working with fuse disconnectors. This includes de-energizing the circuit before working on the fuse disconnector, wearing appropriate personal protective equipment, and using insulated tools. Always verify that the circuit is de-energized using a reliable voltage tester before commencing any work. Lockout/tagout procedures should be followed to prevent accidental re-energization of the circuit while work is in progress. Arc flash is a dangerous phenomenon that can occur when a high-voltage electrical fault creates an arc of electricity through the air. Arc flash can cause serious burns, blindness, and even death. To protect against arc flash hazards, it is important to wear appropriate personal protective equipment, such as arc-rated clothing, gloves, and face shields. Arc flash hazard assessment should be performed to determine the potential arc flash hazards in a workplace and to select the appropriate personal protective equipment. In summary, selecting, installing, and maintaining fuse disconnectors requires a thorough understanding of electrical codes, standards, and best practices. By following these guidelines and taking appropriate safety precautions, it is possible to ensure the safe and reliable operation of electrical systems. This careful approach not only protects valuable equipment but also safeguards the well-being of personnel who work with these systems.